Previously on the head of a pen.
Atoms are not the most basic things. They can be broken up into electrons, protons, and neutrons, so-called subatomic particles. And those protons and neutrons can be broken up even further into things called gluons and quarks.
Our Earth is constantly being bombarded from outer space by high-energy particles that we call cosmic rays.
There is a famous equation called the Schrödinger wave equation. It's a function that has a value at any point in space. All right? It might be 10 here, and it might be 1/10 over there. A German physicist named Max Born, and he reinterpreted this wave function. He said that that is really just a probability wave. That gives me the probability of finding a particle at this point at this time.
Ultimately, our description of nature is just that, a description. And it's important not to confuse the description with the underlying reality for anything. The basic nature of light has been a puzzle for a very, very long time. Isaac Newton, 300 years ago, was puzzling over whether light had some sort of continuous nature or was corpuscular. Obviously, the fact that if you have a source of light, you have a screen, we can make a shadow, right? And that tends to suggest that light has some sort of particle nature. Nevertheless, we can demonstrate that light has wave properties by, sending it through a slit, for example. You'll see light diffract and create little wave-type patterns that we see only with wave nature. So that already started in the early 18th century. But it wasn't until the mid-19th century that it was realized that electricity and magnetism were related to each other, and one could write down a complete theory of electromagnetism, what we now call electromagnetism. That was Maxwell who did that, and that was the first unified sort of theory in physics.
When James Clerk Maxwell took electricity and magnetism, which were thought to be two different forces back in about 1860, and came up with a theory that put them together in the theory of electromagnetism. One of the results of that theory was that he could predict that there was a disturbance in the electromagnetic field that traveled at the speed of light. In fact, this electromagnetic disturbance was identical to light. And at least in the visible portion of the spectrum, the electromagnetic field would send out photons that could affect our eyes. And it was until the 20th century that we realized that these waves that were at the basis of Maxwell's theory also had a particle manifestation. Right? That you could have chunks of light. That was really Einstein's great contribution. That's what he got the Nobel Prize for, not for relativity. All right? Yes, Einstein came up with the theory of relativity and said that nothing, not light, not electrons, not thoughts, couldn't travel any faster than the speed of light. That's the fastest speed that information can travel in the universe. All right? But what he got the Nobel Prize for was not relativity. It was for the graininess of light, that it came in chunks called photons.
How do we go from a description of this type of energy, electromagnetic energy, from being a wave, which is a big continuous thing, the way we think of it, to a photon, which is like a little particle? And the way to think of it, I think, is in terms of this particle having both wave-like and particle-like properties. It's spread out in space a little bit, and it's spread out in energy a little bit. Just a little bit, though, according to the uncertainty principle.
For many centuries, there had been a battle between the two pictures of light. And people like Newton, Isaac Newton, thought light was a particle. He said, well, it creates these sharp shadows. It doesn't really go around corners like a wave, so it must be a particle. And then other people, like Christian Huygens, who was a contemporary of Newton, he was a Dutch physicist, said that light is a wave because it has phenomena like diffraction and and interference and refraction. The fact that you can see these bent images if you stick a rod into water. So there are these competing ideas. At the time of James Clerk Maxwell, the dominant idea was that light was a wave. And along came Einstein in 1905, and he said, no, light is grainy. It's a particle, which we later called a photon. What we now have, after about the middle of the 1920s, when quantum mechanics really became firmly entrenched, we have a sense that light can be either a wave or a particle. It's called wave-particle duality. And it can manifest its waviness in certain situations, and it can manifest its particle properties in other situations, depending on how we set up the experiment. It's a very counterintuitive notion.
Newton showed that you could take white light, separate it into its colors, and then, even better, this shows Newton's genius, you could take that rainbow and recombine it into white light with a prism running it through the other way. And that shows that inherent in light are all the different colors, whatever those colors are. But they didn't really understand what made the colors different from each other until much later, when once the wave nature of light became understood in the 19th century, then things really became controllable and understood much better. It was really the 19th century before we understood that light had a wave nature. And then, only at the end of the 19th century, did we understand that it has this truly particle nature as well. When you have something with a wave nature, they theorized in the 19th century, there must be something that's waving. If we go back to the pond with a piece of wood bobbing in the pond, you have the pond, and that's what is the medium for the wave. So what is the medium for light? And they thought it was the ether, some mysterious substance in which electromagnetism could propagate.
People thought that if you have a wave, if light is a wave, then it's got to have some medium to wave in. A wave is a disturbance in some kind of medium. Water waves in water, the medium is water. Sound waves, the medium is air. So the physicists of the 19th century thought that light is a wave, and there must be some medium called the ether. The luminiferous ether, which was thought to be some very stiff, transparent medium through which the Earth moved as it went around its orbit, and light would, any light waves were oscillations in that ether. All right, and Einstein, with his theory of relativity, essentially shattered the ether. He said, we don't need an ether. If light is a particle, then it can come from the sun to my eye without any need for an intervening medium.
We don't talk about it being a fixed ether with this sort of eternal nature or infinite extent or anything like that anymore. It's the vacuum of electromagnetism is the modern term. We all know what radio waves are, or at least we think we do. People have some picture in their mind of what a radio wave is, but what is it really? It is a disturbance of electromagnetism. The way the universe is apparently set up to work, we have something called electromagnetism, meaning that we can create electric fields and magnetic fields. It turns out if you have a charge just oscillating back and forth, moving back and forth, it creates a disturbance, much like if you take a piece of wood in a pond and just bob it up and down, waves will propagate out from the wood. That's exactly what happens with electromagnetism in our vacuum, the vacuum of free space, if you will. You can make electromagnetic waves propagate. As electromagnetic waves propagate through space, you have an electric field and a magnetic field which is exactly perpendicular to it. So if this is the electric field and this is the magnetic field, as this goes from being up to being down, the other one goes from being left to being right, and they oscillate back and forth like that. And that's what is that disturbance, that positive-negative oscillation, is what is propagating through space. So you can actually measure the magnetic field strength of an electromagnetic wave, like a radio wave or something.
Light can be what we call redshifted or blue shifted. All right, it can change its frequency. All right, depending on the motion of the object from which it was emitted, depending on how the universe is expanding. But it doesn't change its speed. All right, light coming to us from a faraway galaxy, let's say billions of light years away, all right, appears to be shifted from its natural frequency to the redder portion of the spectrum, because space is stretching out. The expansion of the universe is stretching space out. That doesn't change the speed of light. It changes the frequency of the light. If we were in a collapsing universe instead of an expanding universe, and the space was collapsing in on itself, that light would be shifted to the blue end of the spectrum. All right, it would be blue shifted, but it would still be going at the same speed of light.
It's a remarkable fact that it was discovered in the 19th century by Michelson and Morley, ultimately, that even though we are moving with respect to light, whenever you try to measure the speed of light, it's always the same, no matter if you're moving away from the source of the light or toward the source of the light. It doesn't matter. And that's a very weird fact about our universe, and Einstein took that and ran with it.